Okay, so when I was very small, I used to watch a television program, and the program started by saying, if you're all sitting comfortably, then I'll begin. So I hope you're all sitting comfortably. I'd like to say a big thank you, first of all, to everybody who's made it possible for me to visit India this week. I've had a very exciting, interesting, and intensive program. I have met lots and lots and lots of young people, and it looks like today I'm meeting even more. So I'm astonished to see so many Indian young people coming along, interested to listen to talks about CERN, particle physics, and the God particle. I was a bit surprised when I drove up at the gate this morning and saw the title was The God Particle. This is a very controversial name for what we call the Higgs boson, actually. How did that name arise? Well, actually, it was a bit by accident. There's a very famous physicist called Leon Lederman, who was director of a sister laboratory of CERN in the United States, Fermilab, and he wrote a book, and in the first pages of the book he referred to this goddamn particle. And his book producer, editor, read this and said, "You can't write goddamn particle in a book. Let's call it the God particle." And we're now stuck with this name more by chance. We would prefer to call it the Higgs boson. But that's where the name came from. Where do I come from? Well, I was born in the north of England, in between two cities called Leeds and Bradford, both of which have large Asian communities, in actual fact. So I'm quite used, in my younger days, I was quite used to playing cricket with and against young Asian boys who were of my age, okay? And in fact, I was actually destined to be a cricketer. I was introduced by my grandfather and my father to all their friends when I was even 2 years old as a future opening batsman for Yorkshire and England, like Geoffrey Boycott. Okay, I don't know if anybody plays cricket here. Actually, I've not seen anybody this week playing any cricket anywhere in Delhi. I did see one young man carrying a bat, okay? So, but in fact, I did play sport for all of the first part of my life, and it continued actually for quite a long time. I played a lot of soccer, a lot of cricket, a lot of squash. But at the same time, I started to get passionate about science. And I ended up is not the right word really, but I did actually have the fantastic, great, good fortune to have the opportunity to work at this place, CERN. It stands for Conseil Européen pour la Recherche Nucléaire. So which two languages are we supposed to be able to speak if we work at CERN? Hindi and English. French, sorry, that's right. French and English, okay? So we're supposed to be able to speak French and English. And what CERN stands for in English is the European Council for Nuclear Research. And I'm going to tell you a little bit about the story of CERN. I'm going to tell you what we do, how we do it, and a little bit about the famous Higgs boson. Okay, that's what my job is this morning. I'm going to interact with you. I hope I'm going to interact with you. My first attempt at interaction worked very well. So if I ask you a question, please talk to me, okay? I'll get very disappointed if you don't talk to me, okay? So, where is CERN? Does anybody know where CERN is, by the way? Okay, I think I heard Geneva, and Geneva is in Switzerland, so this is where CERN is. It sits at the end of Lake Geneva if you're Swiss, or Lac Le Mans if you are French, because it sits right on the French-Swiss border. And this is the border here, the white dotted line. Switzerland is here, and here you have France, and here you have France as well. So if you walk out or bike out or take a tuk-tuk out of Geneva in any direction apart from this direction, you immediately come to France. Anybody know what those mountains are? Alps, very good. Anybody know what this guy is? Mont Blanc, very good. The White Mountain. It's the highest mountain in Europe, 4,800 meters high. Not very high compared to your mountains. If I take my car and drive to this mountain, it's about 120 kilometers from Geneva. So it takes about the same time as it takes from my hotel to get to this university. Okay? I've been very impressed by the traffic in Delhi, by the way. I've taken lots of photographs to show my friends back home. It's absolutely amazing. Anyway, if I take my car to this mountain, there's a tunnel which is 12 kilometers long right underneath this mountain, okay? And if I drive through that tunnel, which country do I come out into? Again? Italy, yes, we come out in Italy. And so if you want to have a nice pizza or some pasta for lunch, you can jump in your car and drive to Italy and have some there, okay? Why am I telling you this? Because it relates to the story of CERN in actual fact. We'll come to that in a minute. While we've got this slide, we can actually talk about this ring. By the way, I live here, and CERN is there, so it takes me 5 minutes to get to work every morning, and 10 minutes on a bad day. Okay? What is the yellow ring? Okay, good. So, some people say it's the LHC. What is the LHC? Large Hadron Collider. Prachi, where are you? These guys know everything. I don't have to keep talking, okay? We've got some guys coming in. Okay, if you come in quietly, you can walk across the front. Okay, I'll keep talking anyway. The Large Hadron Collider. Now, the question is it really the Large Hadron Collider, that yellow ring? That's right, it's actually not. It's the footprint of the Large Hadron Collider on the Pays de Gex. That's what this is called. This is in France. The Large Hadron Collider sits 100 meters approximately below ground. By the way, why is it called the Large Hadron Collider? Because it's humongously large. It's 27 kilometers in circumference, yes. Why is it a collider? Collides particles together. Which particles does it collide? Hadrons, and specifically protons, and some of you might know it also collides what? Lead ions, heavy nuclei of lead, 82 plus nuclei of lead. Okay, it does that only a month a year, and the rest of the time, apart from a shutdown period, it collides protons. Why is it 100 meters below ground? Well, could you imagine the chaos on the surface if you had this very large particle accelerator that lived on top of the ground? It's actually underneath small villages, could be underneath your back garden. You don't see anything. It has no impact for you. So it's very environmentally friendly. That's one reason. What's another reason? What's a benefit for it being underground? What? Lower temperature. No. Okay, it means there's no problem from radiation. Some of you may know that if you have a charged particle and you accelerate it in a circle like this, it emits radiation called synchrotron radiation. That radiation is dangerous. But when the accelerator is operational, nobody is below ground, and it's 100 meters below ground, so there's no problem. Okay? We can come back to that later. And finally, the accelerator itself is very, very, very heavy. So you have to locate it in a geological strata which will take the weight. And 100 meters below the ground, in this region, there's a rock strata which will take the weight of the accelerator. It's a fantastic seismic measuring machine, by the way, but that's a detail. You can talk to me about that afterwards if you wish. Okay, so that's where it's located. This slide, we've already talked that we have to be able to speak 2 languages at CERN. This is somewhere in Europe in 1945 after the end of 2 devastating world wars. Does anybody study French? Okay, so you can translate for me what this says on the bottom. Well, I can't hear you, but I am assuming that you've got it right. It means that in those days, many scientists, European scientists, were leaving Europe, and it was called the brain drain, and going to work in the United States because there was no laboratory, no facility for them to do their research in Europe. And this prompted some very famous physicists, Louis de Broglie, that's the French way to pronounce his name, Werner Heisenberg, Niels Bohr, Robert Oppenheimer, director of the Manhattan Project, to get together and say, we've got to stop this. The intellectual capacity of Europe is bleeding towards the United States. How can we do this? And they came up with the idea of building a laboratory in Europe which no single country could afford, getting countries to club together and to attract the researchers to stay. They proposed this to UNESCO, and surprisingly, they did this in 1948, 1947, 1948, 1949, very important time for India, and it actually happened. And if we say it was 1949, 5 years later, CERN was founded, remarkably. Very, very short time. And it was located in Switzerland. It was located in Geneva. Why? Well, at the time there was the League of Nations, which was the forerunner of the United Nations. It's Switzerland, neutral country, and also central in Europe, as I've just shown you from our geographical description at the beginning, discussion at the beginning. 12 European states signed up in 1954 Today we have 22 states. Notice I didn't use the word European, okay? Israel is not in Europe, and we have associate members, including India. India recently became an associate member of CERN. So we have to change the name, but we can't change the acronym, really, and we can't really change the name because it's written in a legal document. But we can sort of think of it in a different way. So if we had to change the E from European to something else, what would you choose that began with E? Eurasia. Well, the previous, not this today's Director General, started saying it should be, we can say everywhere. Okay, so that's a good replacement for E. And I was talking to an Indian group of students not long ago, which were brought to CERN by the Life Lab Foundation. And a young lady in the audience said, you could replace the Europe with Earth. And I thought about that, and I thought, that's a really good idea. It sounds like Star Wars, the Earth Council for Nuclear Research. Fantastic idea. So whenever I talk to people now, I give it this name, and I say thank you to the Indian young lady who had the idea. We don't like, actually, one word in that name. Which is the word we don't like? Nuclear, that's right. We're not so keen on the word nuclear. What does nuclear make you think about? Bombs, for example, and nuclear power generation. We're not into making bombs, absolutely not at all. And we don't do anything associated with nuclear power generation. In fact, we use nuclear power because the electricity that we use to power the accelerators and the equipment at CERN comes from France. It's exactly the same electricity or source as I use to boil my egg in the morning. It just comes from the French grid, and the French grid is 80% nuclear power, in actual fact. So we don't like the name so much, so we call ourselves the European Laboratory for Particle Physics. That's a mouthful. It's not a good acronym, so we keep the acronym. Okay? So here are the countries, Here are the countries who are now member states of CERN. We have the associate member states, and you can see it really is a world laboratory. Who works at CERN? Well, we have 2,500 members of personnel. We have 1,800 other people. And very, very importantly, 13,000 scientists come to work at CERN from all over the world, including India. Okay? What's our budget? Our budget is actually 1 billion Swiss francs, which I think is 70 billion rupees. Is that right? Something like that. Is that a lot of money? Well, it's a lot of money for my pocket, okay? But how do we compare it? What do we compare it to? I don't have it in my pocket. It's in my bag. I have a phone, like you've all got phones today. Did you know that the WhatsApp application that runs on your mobile phone was bought by Mark Zuckerberg? Do you know Mark Zuckerberg? Personally? You heard of Mark Zuckerberg. He bought the WhatsApp application for 19 billion Swiss francs. For me, this is totally crazy, okay? That's 19 years of the CERN budget, or 4 LHCs, 4 Large Hadron Colliders. So what's a better comparison? Well, a better comparison may be that it's about the budget of a medium-sized European university. Now, where does everybody come from who works at CERN? Well, they come from all these countries. And you can see there are more than 100 nations represented at CERN. More than 100, including India here. So something like 350 scientists from India work in association with CERN. What do I mean is that they're attached to Indian universities or research establishments or other universities around the world, and they do science associated with CERN. They come to CERN, they do experiments at CERN, they stay on the site. We are the biggest hotel in Geneva. We have 500 beds for visiting scientists. Okay? So they come. Now, the blue, the color codes are simply, these are the member states. The light blue are the associate members. And the red guys are the others. And you can see they actually come from everywhere. So it really is the Earth Council for Nuclear Research or Particle Physics. What else can we say about this? Actually, the interesting question is, who do we actually work for at CERN? Do we work for the 22 member states that pay our budget? By the way, they pay according to gross domestic product. So Germany pays 23%, Italy, France, and the UK pay about 15%, and Hungary doesn't pay so much. But they all have a single vote on the CERN Council. So it's a very democratic organization. But who do we really work for? Progress? We actually work for humankind. And this is a really big, important message for you. All the research that we do, we publish, and it's available to everybody. And when I mean research, I don't only mean research in fundamental science and fundamental physics, but I mean the research that we do in order to be able to conduct the research, and we'll come back to that. So, we work for humankind, okay? And all of these people work together. They don't fight each other. In other circumstances, they might be doing that. But at CERN and in the particle physics community, we're focused on fundamental research, technological development for humankind. We collaborate with everybody. Very important message for you, that one as well. Okay, so what are our strategic missions? What are the strategic missions of CERN? If I to ask you what do we do, what would you say? I'm going to ask you again in a few minutes. So I'm going to ask you, what 3 questions has humankind been asking for thousands of years? We don't ask them now, I'd say in a couple of minutes. They appear on another slide. What 3 questions? And basically we do fundamental research to answer these 3 questions. So we're trying to understand our universe, push back the frontiers of knowledge, etc. So that's one that I think you would probably all write down. But we have another 3. The next one is to actually develop the technology to do that. When the CMS experiment, the compact muon solenoid, which is on my t-shirt, I've been wearing another t-shirt all week, but I put this one on today. This is the compact muon solenoid. When that was first thought about in the 1980s, the technology to do that experiment did not exist. So what did the guys do? And when I say guys, I mean the American interpretation of guys, which is ladies and gentlemen. Okay? So, what did the guys do? They went to sleep, okay, for 25 years, and when they woke up, they could do the experiment because the technology had been developed. Is that right? Is it right? No. They developed the technology. And if I were to ask you, or if you were to ask me, is the Higgs boson useful? Is the discovery of the Higgs boson useful to me? I would say to you, I have no idea. The people who are going to answer that question are sitting here in this audience, or they are your contemporaries sitting in other universities, in other schools around the world. So we don't know today, but what we can say is the technology that has been developed to discover the Higgs boson is already being used outside universities and experimental research laboratories. An example of that, I normally wear the t-shirt, which is an example of that, which is quite close to me personally. It's a t-shirt which has the diagram that Tim Berners-Lee submitted to his supervisor in 1989 with his concept of the World Wide Web. Okay? The World Wide Web was invented at CERN in 1989 and given to the world. How much did CERN charge the world for the World Wide Web? 20 billion? 50 billion? 1,000th of a rupee for every web page that has ever been loaded? Nothing. We gave it to the world for nothing. Okay, the supervisor took this diagram away, looked at it over the weekend, and he wrote 3 words on the top of the diagram. Can anybody guess what the 3 words were? Have you heard me before? Yes, so we have some people who've been listening to me this week before. He didn't write World Wide Web or this won't work. He actually wrote something which is normally on the back of the t-shirt. He wrote the words vague but exciting. Now I think those words are probably the understatement of the 20th century, if not of all time. Okay? And I have the great pleasure not only to meet young people like you, but to show people around who come to the laboratory at CERN. So, for example, I've shown Buzz Aldrin around CERN. Who's Buzz Aldrin? The second man to walk on the moon. He came in his Apollo 11 jacket, his tie, and he was very excited and he really enjoyed his tour. I've also shown around Kofi Annan. Who's Kofi Annan? Ex-Secretary General of the United Nations. And when I took him round, I wore the Web t-shirt. And when I said, hello, welcome to CERN, this is what we're going to do. And he said, what's that? Pointing at my t-shirt. And I told him the story I've just told you. And he said to me, that supervisor was a very good supervisor. And I said, yeah. He didn't say, your idea is nonsense. It's not interesting. It's not technically feasible. You shouldn't be doing it. Get on with your real work. He encouraged him, and today we have the World Wide Web, thanks to that. Now, when I talk to young people in an audience like this, I say, actually, I changed the word supervisor into something else. What do I change it into? Begins with T. Anybody got any idea? Teacher, yeah, well done. So I changed that word into teacher because those are the qualities of a good teacher. And I'm sure that all the teachers in the audience that are here today who've brought you here to this seminar are good teachers. And I always say it's time to give them a big thank you. So give a round of applause for your teachers. Teachers hold the future in their hands. You, okay? So, that's the story about the World Wide Web. But not only the World Wide Web. What two big tools do we use to do particle physics? Any idea? Sorry? An accelerator, that's right. We take a proton, we ring up Amazon.com, we order a bottle of hydrogen, we pull the electron and the proton apart, we throw the electron away, and we accelerate the proton. Okay? So, we use accelerators, and what else do we use? Detectors. Detector? Fire detector. No. What's another word for detector, which gives us a better image of what it is? It's a camera, a very complicated camera. And you're going to hear more about the camera later on this morning. So it's a camera that takes pictures of the collisions of the protons and what happens when they collide. Very sophisticated camera. Now, both of those instruments are actually used today in the medical field. So those of you who want to be doctors, by the way, anybody want to be a doctor? Okay? Anybody even thinking of being a teacher? Great, there are some people who are thinking of being a teacher. Congratulations, very important career. Okay, used in medicine, you can use the camera, the detector, to look inside your body to locate a tumor, and you can use the particle accelerator to zap it, to kill it. And it's more effective than using X-rays and less dangerous for you. But that's another story. But if you want to know about that, you can ask us questions. Medical applications of particle physics, very important. So those who've transferred into the outside world. Third strategic mission is to training these scientists and engineers of tomorrow, or inspiring them. That's my job today. Try to encourage you to continue your scientific education. Okay? And finally, uniting people from different cultures and countries, 100 nations all working together, collaborating, maybe not able to speak to each other very well, but getting their ideas across, often using the universal language of science, which is mathematics, okay? That's the fourth strategic mission. A little bit of science now. The whole universe was in a hot, dense state, and nearly 14 billion years ago, expansion started. Wait! Okay? We think it all started with a Big Bang. Go, Sheldon, go, all right? Big Bang, 14 billion years ago, 13.82 billion years ago, according to the latest results from the Planck satellite. And what we are trying to do is study our universe and ask these three fundamental questions, which we're getting very close to telling you what the three fundamental questions are. On a ruler, which is very long, we live at the scale of a meter. You recognize yourself. There you are. Who's that? Good, Albert Einstein. And if we want to look at the very big, the very far away, we use our telescopes, the VLT in the Atacama Desert, the Hubble telescope, fantastic instrument, had to be repaired by astronauts. And they did it in space. Anybody want to be an astronaut? Wow, great. I've met many astronauts, actually. They've come to CERN because we have a particle detector attached to the International Space Station. And I've had the great privilege of showing them some of the facilities of CERN. Very cool people, actually. Very cool people. If we want to look at the very small, what do we use? Microscope. What's our best microscope? It's actually the LHC. It's actually the LHC. And what do we know? We know that matter is made of molecules, atoms, nuclei, protons, neutrons, quarks and gluons, maybe something else. There are always open questions, guys, always open questions. When I started in this game, this field, the two ends of the spectrum, studying the two ends of the spectrum were very separated. In fact, cosmology was very, very newborn subject, really. But today, we put them together. If you talk about the very small and the very big, studying cosmology and studying the very small, I give you combined information. Okay, so that's the two subjects have come together. Okay, now we get to the three questions. Who painted that? Question 0. Anybody know who painted that? My friend on the front who talked about the arts and the association of arts and science, which is very important, actually. I am going to present a book to somebody that I don't know yet. I brought a book with me that illustrates the connection between the arts and science, which was written by a very good friend of mine. I'm going to present that to somebody. Anybody else know who it was? Famous French artist, lived at the beginning of the last century. His name is Gauguin. Gauguin. And he knew what the three questions are that humankind's always been asking for thousands of years. And he wrote them in French. Here. Okay? Anybody idea what they are? Where do we come from? How did it all start? How did the universe begin? One question. Sorry? Who is our creator? That's a question that people have always been asking, but I don't think by doing particle physics we're going to answer that one. We have to ask somebody else the answer to that question.
Why are we?
Sorry?
Why are we created?
Why are we here? My answer to that is the same. We can't answer that. We have to ask somebody else. But we can ask, where are we going? How is the universe evolving? And we can ask, what are we made of? So where do we come from? What are we made of? Where are we going? And I always say at this point, there's a fourth question that humankind has always been asking, very important. Woody Allen reminds us of it. What are we having for lunch today? Okay? We can't answer that one, but I have to keep talking, otherwise we won't get any lunch. So let's move on. So those are the questions. Where do we come from? What are we? Where are we going? To do it, we built this thing called the Large Hadron Collider. Here it is, sitting in its tunnel, 100 meters below ground. If you go down there, when the accelerator is not running, you can walk along here, you can touch the components. The temperature's 20 degrees, there's lots of air to breathe. If you have to do some work down there, how do you get to work? There are only 8 access shafts around a 27 kilometer circumference ring. So you get up in the morning, you say, I want to work between point 3 and point 4. I'll go down lift number 3. But I've still got 3 kilometers to go to work. How do I get to work? We have rickshaw drivers down below ground. No, we don't. But you can take a bike, a small bike, and ride along here. No roller skates or roller blades, too dangerous. And if you want to take heavy equipment, you can have an electric cart. What we do in the collider, we collide protons together at 6.5 tera electron volts each, okay, in opposite directions. What's a tera electron volt? 10 to the power? $12. Okay. I won't ask you what an electron volt is then. It's the energy acquired by an electron when it falls through a potential difference of 1 volt. Okay? Billion collisions per second. Billion collisions per second around the ring. What are we trying to look for? Answer the questions. What's the origin of mass? This is connected to the famous Higgs particle. Okay? That's connected to the famous Higgs particle. What is the nature of dark matter? What is dark matter? Does anybody know? Well, that's a trick question, because if you do, you will have a Nobel Prize. Okay? It's the stuff that we don't see, but the stuff that exerts a gravitational effect upon our universe. It makes up 23% of our universe, dark matter. We are only 4%. And the rest is something we've no idea what it is. It's called dark energy. What did the universe look like right at the beginning? And why do we see no antimatter? Big Bang Theory says equal amounts of matter, antimatter, but when we look everywhere, we don't see any antimatter. Where's it all gone? Very interesting question. The accelerator is very empty. In the tubes in which the particles run round, the pressure is 10 times lower than on the moon. It's also colder than outer space because the whole accelerator, the whole of it, inside is kept at 1.9 degrees Kelvin. It's filled with liquid helium. Why? If you want to know the answer to that question, you have to ask me. Okay? It's colder than outer space as measured by the cosmic microwave background radiation. This is the temperature difference of our universe as seen by cosmic microwave background radiation. And that is a fantastic diagram. It's not the latest one, but that tells you many different interesting things about our universe. Okay? Where is the LHC? 100 meters below ground. Here's the lake. Here are the Jura Mountains. Okay? Jurassic Park is here. All right? And we have the LHC with its 4 experiments, Atlas and CMS, LHCb, and ALICE. Here are the experiments when they were under construction. This is the little guy here. This is the Atlas experiment, the CMS experiment, ALICE, and LHCb. The 2 big discovery experiments. Why do we have 2? If you want to know, ask me. ALICE and LHCb, primordial plasma and matter-antimatter difference. How big are they? Well, that's Germany. That's the Brandenburg Gate in Berlin, and that's the size of the Atlas experiment. It's bigger than CMS, but CMS is heavier. So it sits in a big cavern 100 meters below ground. This auditorium might be about 15 meters high, so the CMS experiment would just about fit in this auditorium. Maybe it's a bit smaller than 15 meters. CMS is 15 meters in diameter and weighs 14,000 tons. We say it was the hottest place in the galaxy. When the particles collide, they have the equivalent temperature, 1 billion times higher than in the heart of the sun, but nothing gets hot. We don't call the fire brigade. It's okay. It's only an equivalent temperature. Now, in order to do this, to accelerate these particles to really high energy, we can't do it in a single accelerator. You have to go through the gears. So you have to have multiple, we have an accelerator chain, and like in a car, And here's a schematic diagram. So we have the LHC, it's not to scale, but the bottle of hydrogen is here, and the particles are accelerated in a straight line, linear accelerator, and into a circular, small circular accelerator, into another guy, under the road that connects France and Switzerland, into the fields, and then some kilometers in circumference, and then finally in opposite directions in the LHC. This guy was built in 1959. It's the heart of CERN. It's still beating as I'm talking now. It was built to last maybe 10 years. Fantastic tribute to the guys who built it. Remember, in science, we rarely start with a blank sheet of paper. You stand on the shoulders of the giants who have gone before. Let's start the whole accelerator chain, shall we? Okay, here we go. Red beam, blue beam, into the LINAC, the booster, the proton synchrotron, superproton synchrotron, and finally, bang! Collisions. Is there a bang? Well, it's in a vacuum, so if there was a bang, you wouldn't hear it, but there isn't a bang, okay? So there we go. One more time. Not a single particle, by the way. 2,000 bunches, each with 100 billion particles in the bunch, running around the ring. What happens when the bunches meet? 100 billion particles meet 100 billion particles. What happens? Most of them don't see each other. The cross-section of the beam is the cross-section of a human hair. You take a human hair, you accelerate it, and you collide it with another human hair. As you can see, I've done this demonstration for CERN many times. Professional hazard, this is. Okay, what happens? They don't see each other, most of them. Why? Because protons are really, 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 really tiny. But nevertheless, you get 40 million collisions per second. 40 million collisions per second up at CMS or at Atlas here. And guess what? Most of them are not interesting. So you throw them away. So you have electronics and software that's been built or has been written by guys like you, just like you. Remember, to work in particle physics or in many fields of physics, you don't need to be Peter Higgs. Peter Higgs could not have built this. Stephen Hawking could not build the CMS experiment. It's built by people like you. So you have a place, okay? We throw them away. So there's electronics and software saying, no, 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 maybe. Keep this one and look at it. So you have to know, to some extent, what you're looking for, all right? And this is what happens when the particles collide. They smash together, and we have this thing called the detector. This is a generic detector. It's a cylindrical onion. It's made of all these sub-detectors, and they all have the job of trying to identify and study the properties of the particles that are produced in the collision that didn't exist before. Do we see all of the particles? No. For example, we don't see the neutrinos. We infer that they're there. Fundamental law of physics, conservation of energy and momentum. There might be something. We don't also see the Higgs boson because it decays too quickly. You have to infer it's there from its daughters, its sons, its granddaughters, its grandsons that it decays into. And for example, if we created a dark matter particle, we wouldn't see that either. We'd have to infer it was there as well. Okay? This is what the beam crossing looks like. More than one interaction. And this has to be, you have to find this needle in this haystack. That might be a Higgs boson decaying into 4 heavy electrons, 4 muons, okay? Who does that? Electronics, software, written by you guys, okay? We produce about 20 petabytes of data of each year. Anybody a computer geek freak? We must have lots of computer geek freaks in the audience here. You're just not admitting it. Well, this data is analyzed on something called the LHC computing grid, which is actually 500,000 computers, just PCs like you have in your home or in your school, distributed all over the world, connected by high-speed networks. So it's a distributed computing system. Okay? That's how we analyze the data. Okay, particle physics and innovation. I'm going to skip these slides because Ashana is going to talk about them. And I want to go, that's the medical applications, just again to tell you that we can zap tumors, not we, but accelerators can zap tumors, and we can locate them using particle detectors. Medical applications, very important. These are our education activities. We have lots of programs for young people like yourselves. When you get a little bit older, you can come and participate in these programs. India is an associate member, and we'll talk a little bit more about that later. These are the we have programs for teachers. LifeLab wants to bring teachers, physics teachers, to CERN. You'd be extremely welcome. As I say, teachers are really important people, and the first thing we say to them when they arrive at CERN is, thank you for the great job that you're doing. Okay? Summer students. Who works at CERN? Well, yes, we do have physicists. We have experimental and theoretical physicists. But those paid by CERN, there are not so many. Maybe a couple of hundred actually paid by CERN. Bulk of CERN scientific staff are applied physicists and engineers who build the tools, build the facility, operate it, etc., etc. The physicists who do the particle physics are the users, the 13,000 people who come from all over the world. And in between, we have other people, but notably for you guys, all of these are young people, not much younger, not much older than you. And these are the possibilities for you to come and work at CERN for a short time or a longer time. Actually, I went to CERN in 1975 for 1 year. And I stayed for nearly 40. Okay? So what happened? They switched the LHC on the 30th of November 2009. In the 2011, both experiments, Atlas and CMS, started saying, hey, 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 we are getting interesting, tantalizing hints. Maybe we are getting close to discovering the Higgs particle. Okay? But they didn't say they had discovered it. And then on the 4th of July, 2012, they said, yes, I didn't have the photograph of the Directors General, but there was a big meeting in the main auditorium which was broadcast to the world, and the 5 Directors General who were there all said, yes, we've discovered it. Statistically significant signal shown here in the channel, one of the channels which discovered the Higgs boson. What you do is you look for interactions which have 2 photons or maybe 4 muons. You calculate the mass of the particle if it existed that could have decayed into those 2 photons. You plot that mass. If it's just a random combination, it will be flat background. If something was preferentially being produced, there will be a statistically significant bump. Both Atlas and CMS saw exactly the same bump at the same mass, 125 GeV, and so they were able to say, yes, we found it. That's why there are two experiments, by the way. A single measurement in physics is not a discovery. Somebody has to corroborate that, okay? And they could both say it simultaneously. The lady that announced this result for the Atlas experiment is now the Director General of CERN. The first ever lady who's been a Director General of CERN. Fabiola Gianotti from Italy, okay? Here's my picture. There it is. The 5 ex-directors of CERN. Chris Llewellyn-Smith from the UK, Rolf Dieter Heuer from Germany, Herwig Schopper, 90 years old, from Germany, Luciano Maiani from Italy, and Robert Aymar from France. And sitting on the front row here is somebody that Tashana and I see every day in the building where we work. Is Daniel De Negri. He was one of the 5 people who sat down in the 1980s and sketched out his concept for the CMS experiment. And in the audience sitting over here were Peter Higgs and François Englert, who wrote their papers in 1964, predicting the existence of the Brout, Englert, and Higgs field. And Peter Higgs added, he pointed out that having a field would implicate that there would be a particle to look for. Okay, so that's why it's actually called the Higgs boson and not the Englert or Brout boson. The field is called the Brout-Englert-Higgs field. The particle is called the Higgs particle. Now, why is Mr. Brout not there? These guys received a Nobel Prize. It's because Mr. Brout could not wait. He died in 2011. And you can only give a Nobel Prize to 3 people, and you can't give it posthumously. So the Nobel Prize Committee, I think, did something very elegant. They gave a Nobel Prize to Peter Higgs, François Englert, and they left a space for Robert Brout. Okay, I'd like to say a big thank you